Greetings, beautiful people. Welcome back to Fine XYZ. Kindly subscribe and hit the like button. Always try to leave a comment wherever you are watching us from, the school you are in, any other concept you want us to tackle. We'll do that for you. Given 2 times 2 times 2 times 2 times 2 times 2 a number of times. Is there a better way of expressing this without repeating 2 a number of times? Fortunately, yes. Save us all the time and effort you use in writing 2 times 2 times 2 times 2 times 2. That brings us to our concept of the day, which is known as indices, commonly referred to as power of natural numbers. So we realize that 2 is repeating itself a number of times, so it means that we can just write the 2 because it's repeating. There's no need for us to write it over and over again, right? Then we'll count the number of times 2 is repeating, or the number of times 2 is multiplying itself. Now how many times? Let's count. So we have 1 2 3 4 5 6. So it means that 2 is multiplying itself 6 times. All right, so this is known as the base and this is known as the power. Alright, so giving 2 to the exponent 4 or 2 to the power 4, the interpretation is that 2 is multiplying itself how many times? 4 times. So we can expand this as 2 times 2 times 2 times 2. 2 to the power 4 can be written as 2 times 2 times 2 or 2 to the exponent 4, which is way simpler and faster. Let's try another one. Let's assume I have 1.5 to the exponent 3. Now what is the base number? Now this is the base number. Whatever is here, the base number is 1.5. So I can express how many times is 1.5 repeating itself. That is 3 times. So I have 1.5 times 1.5 times 1.5. The last one before we move on to the next section, which is 3x all squared. What does this mean? This means that this is the base, which is 3x, is multiplying itself 2 times. So we just repeat 3x 2 times, which is 3x times 3x. So that is how it works. Let's dive in to the next section. Imagine we have 3 to the power 2 multiplying 3 to the power 4. We can express 3 to the power 2 as 3 times 3, and then 3 to the power 4 as 3 times 3 times 3 times 3. Now you realize that it is just one operator. We have multiplication all through. We can just write the base, which is 3, and then how many times? How many times are we multiplying 3? Let's count 1, 2, 3, 4, 5, 6. So I'll write it as 3 to the exponent 6. Alright, so what does this tell you? This is telling us that, let's look at it from this angle. Looking at the powers, 2 plus 4 will also give us 6. So we have 3, 2 plus 4, which will give us 3 to the power 6. So instead of expanding it and writing, imagine you have, let's assume you have 3 to the power 10 times 3 to the power 15. Are you going to expand this and also expand this as well? You realize that that is going to be a huge tax. That is going to be a huge tax. So this is telling us that anytime the bases are the same and they are multiplying, what can we do? We can just write the base, which is 3, and add the exponent. Now we have 3 to the power 25. Imagine multiplying 3 25 times. That is going to be a huge tax. So once we can generalize that, when we have the same base multiplying, the key word is that the same base should be multiplying. We can just add the powers. We keep one of the base and we add the powers. So we can generalize as, let's say, a certain number a to the power m multiplying another number, the same base, will a to the power n. We can just write a and then we add the powers as m plus n. Take note of that. So let's take example 1. So given 5 to the exponent 3 times 5 to the exponent 4, what can we do? From this rule, because the bases are the same and they are multiplying, the bases are the same and they are multiplying, we can just write 5. And what is the first exponent? 3. What do we do? Should add them. So I'll bring plus, and the second power is 4. What is 3 plus 4? That will give us 7. Alright, the next one, giving 2 to the power 4 times 3 to the power 4. What is it going to be? Can we put them together? The key thing is that this base must be the same as the second base, but you clearly see that this is 2, this is 3. We cannot put them together. They are different bases, so this will not work. Be very careful. Another example that I want us to take is, what about if I have 3 to the power 4 plus 3 to the power 3? Can we apply this rule? Can you guess? Can we apply this to this? If your guess is no, then you are right. Why can't we apply this rule? You realize that the operator in between these two terms is addition. What is the operator here? Multiplication. So it will not work when the operator is addition. It has to be multiplication and from the same base. Let's move on to the next one. What about if I have 3 to the power 4 divided by 3 to the power 3? I can clearly expand 3 to the power 4 as 3 times 3 times 3 times 3. That is 4 times. All on 3 to the power 3 means 3 is multiplying itself how many times? 3 times. So I'll write 3 times 3 times 3. Alright, can we simplify? Yes, we can simplify. So 3 divides 3, 1. 3 divides 3, 1. 3 divides 3, 1. So we have 1 times 3. That will give us 3. Alright, now is there a way we can find out, or we can operate this without expanding it using indices? Yes. So look at the powers. Then again, I can write 3. How can we get exponent 1 here? By subtracting, obviously. So we have 4 minus 3. That will give us 3 to the exponent 1, which is the same as 3. How do we generalize? We generalize by saying that anytime we have the base dividing, you see this time they are dividing, we can keep one of the base and subtract the powers. So let's generalize it. So if I have a to the exponent m divided by a to the exponent n, I can just keep the base and subtract the powers. So this is what we have. I can just keep the base and subtract the powers. Then what is the operator? Division. Or I can write it as a to the exponent n and a to the exponent n. I can write it as a m minus n. Let's take example. Alright, so given 5 to the exponent 4 divided by 5 to the exponent 3, what can I do? What is the operator? Division. Division means, what should I do? Clearly I should subtract. So I can write one of the base, which is 5. Then I'll subtract the powers, which is 4 minus 3. That will give us 5 to the exponent 1, which is the same as 5. Let's try another example. So if I have 6 to the power of 5 divided by 6 to the power of 2, what can I do? Because the bases are the same and they are dividing, I can just write 6 and subtract the powers, which is the first power of 5 minus 2. That will give us, which is 6 to the power of 3. When will it not work? Let's assume I have 6 to the power of 5 minus 6 to the power of 2. Can we subtract? The only time we can subtract, they have the same base, alright, but what is the operator? Subtraction. So this will not work. So it has to be division and the bases must be the same before you can subtract the exponent. Let's move on to the next thing. Now given 3 to the power of 4 divided by 3 to the power of 4, what are we going to get? We can write it as 3 times 3 times 3 times 3. 4 times, yes, this is also 4 times, so 3 times 3 times 3 times 3. You realize that each of them divides each other 1 time, so this will give us 1. This will give us 1. Now let's use the idea that we learned in the previous section, which is anytime the bases are the same and they are dividing, we can subtract the powers. So clearly we can write 3 to the power of 4 divided by 3 to the power of 4. We can just write one the base, and what do you do to the powers? Because they are dividing, you can subtract, which is 4 minus 4. And what is 4 minus 4, which is 3 to the power 0. But what did we get when we expanded it? We had 1, so it means that 3 to the power of 0 will give us what? 1. Now let's try with another number. So let's assume we have 5 to the power of 3 divided by 5 to the power of 3. If we expand, we are going to get 5 times 5 times 5, all on 5 times 5 times 5, which will give us, this cancels, divide that, so we have 1. Using the idea of division, we can write 5 to the power of 3 divided by 5 to the power of 3. What do? We write the base, subtract the powers, which will give us 5 to the power of 0, and this is also giving us 1. So what can you generalize? What we can generalize is that anytime you have a base to the exponent 0, we are going to get 1. Why are we getting 1? We are getting 1 because when you subtract the powers and they are the same, it will give you 0. And when it gives you, anytime the numerator is the same as the denominator, you're always going to get 1. So we are getting 0 because the numerator, the exponent of the numerator, was the same as the exponent of the denominator. Example, if you have 2 over 2, we are going to get 1. If I have 5 over 5, I'm going to get 1. So you realize that because division, we subtract the bases, we are going to end up getting 0. Keep that in mind. So if I give you 10 to the power of 0, what are you going to get? You're going to get 1. Let's move on to the next section. Given 3 to the power of 4 over 3 to the power of 5, you realize that the first one, the numerator, was the power of the numerator was the same as the power of the denominator, and we had 0. This time, let's expand. So the numerator will give us 3 times 3 times 3 times 3, that is 4 times. The denominator will give us 3 times 3 times 3 times 3 times 3. How many times? 5 times. Great. Now let's simplify. 3 divides 3, 3 divides 3, 3 divides 3, then 3 divides 3. What do we have left? The numerator is giving us 1, the denominator is giving us 3. So we have 1 over 3. Now let's use the idea of dividing exponents to solve this. So we can write 3 to the power of 4 divided by 3 to the power of 5. What can we do? Because they are dividing, we can write the base and then subtract the exponent. So we have 4 minus 5, which will give us 3 to the power negative 1. Now it means that when we have 3 to the power of a negative number, what can we do? It is giving us 1 out of 3. What does this mean? It means that when we have a negative exponent, so let's assume I have a to the power of negative m, I can write it as 1 over a to the power of m. So it means that what we do is you swap and then change the sign of the exponent. So an example, whenever you are given 4 exponent negative 2, what can I do? I can write 1 over 4. Because I've swapped the position of the 4, I have to change the sign, and changing the sign giving us positive. Okay, so anytime you have a negative exponent, you can write it as inverse, right, and bring it down. Change the position and change the sign. Change the position and change the sign. Another example, what if you have 2 over 3 to the exponent negative 5? Now we are changing the position. Is that not it? You realize that the position of this is 2. We'll change the position now. It becomes 2. We bring it down. The position of this is down. We bring it on top. Then what do you do to the exponent? We change the sign. So you realize that the same way, this is also over 1. So if I flip it around, I change the position, I change the sign. So the same way, you change the position of the numbers and you change the sign. So if it is positive and I change the position of the bases, I have to change the sign of the exponent. The next section. Alright, so giving 3 to the exponent of 2 to another exponent of 3. Now we are saying that indices is repeated multiplication. It means that 3 to the power of 2 is repeating itself how many times? 3 times. So we can expand this as 3 to the power of 2 times 3 to the power of 2 times 3 to the power of 2. What can we do? The bases are the same and they are multiplying. This is multiplication. This is also multiplication. What can I do? I can just write the base, which is 3, and then what do? I add the power. So I have 2 plus 2 plus 2. That will give us 2 plus 2 will give us 4. 4 plus 2 will give us 6. So we have 3 to the exponent of 6. Is there any way of arriving at 6 without expanding? So look at this. I can clearly just write 3 to the power of 2 times 3 then I can write it as 3 to the power of 6. So you realize that they are giving us the same value. So what can we generalize from this? What we can conclude is that anytime I have a to the power of n to another exponent, let's say n, I can just write a to the exponent m times n. I can just multiply the exponent. I can just multiply the exponent without expanding. An example. So given 3 to the power of 2 and let's say 5, I can write it as 3 to the power 2 times 5, which will give us 3 to the power of 10. Or if I have x to the power of 2, x to the power of 2 to the exponent of 5, I can write it as x to the power of 2 times 5, which will give us x to the power of 10. Given 3x to the power of 4, same way we can expand, is that not it? How many times are we multiplying 3x? That is 4 times. So we can expand this as 3x times 3x times 3x times 3x. You realize that the 3, we have 3, we can write it as the base. Let's count 1, 2, 3, 4. Is that not it? So we have 3 to the power of 4, and then we have x. That will give us x to the power of 4. When you have two terms multiplying, a product of two terms and an exponent, you can distribute the exponent to the bases. It has to be a product. Example, if I have 3 times 5 to a certain exponent which is 3, I can write this as expanding. 3 times 5 is repeating 3 times, right? So I have 3 times 5 times another 3 times 5 and another 3 times 5. Now let's group all the 3s. So we can have 3 times 3 times 3 times 5 times 5 times 5. Now how many times are the 3 multiplying itself? 3 times. So I can write 3 to the power of 3 times how many times is the 5 multiplying itself? That is 3 times, that is 5 to the power of 3. So instead of expanding all these, I can just distribute the powers to them, and I can write this as 3 to the power of 3 times 5 to the power of 3. The key thing is that make sure that it is a product of two terms. 3x is the same as 3 times x. That is why I was able to apply the same rule. So the same thing, once it's multiplication of two terms, I can just distribute the powers to them. So let's take an example. So given 2x to the exponent of 5, 2x means 2 multiplying x, so I can distribute the exponent to the x and to the 5. So I can write this as 2 to the exponent 5 and then x to the exponent 5. So in conclusion, we can summarize this as a b to the power of n can be written as a to the power of n and then b to the power of n. So anytime we have a product of two terms and an exponent, you can distribute the exponent to the terms. Given 3 on 2 to an exponent 3, we can expand because the base is multiplying itself how many times? 3 times. So we can write this as 3 over 2 times 3 over 2 times 3 over 2. Now how many times is 3 multiplying itself? That is 3 to the power of 3. And how many times is 2 multiplying itself? That is 2 to the power of 3. Clearly we can see that we can also distribute the powers to each term. 5 over x to the power of 4, I can distribute it as 5 to the power of 4 over x to the power of 4. We generalize that anytime I have a over b to an exponent n, I can distribute the powers to each of them. I can have a to the power of n over b to the power of n. Simple as that. So when I have a fraction, I can distribute, or you have a ratio of two numbers, or two numbers are dividing, you can distribute the powers to them, and it always work. You can clearly see from the above example. If I have a fractional exponent, so realize that we have done negative exponent, we have done zero exponent, we have done positive exponent. What about if the exponent is a fraction? Alright, so given 25 to the exponent 1 over 2, You can clearly see 25 is a square number, so I can express 25 as 5 squared to the power of 1 over 2. Is that not it? Then the exponents, we can multiply them from our previous section. We have 5, 2 times 1 over 2, that will give us 5. Now this can be written in another way, which you are very familiar with. Now we can write this as square root of 25. Now there's a 1 here and there's a 2 here. The symbol is the same as the 2, so there's no need to repeat the 2. But the thing is, this is called the root. Then giving an example of a plant, you realize that the root is always down, the root. So taking inspiration from that, we can bring the root here, we can bring the root down of the exponent. So we can write this as 25 1, then we'll bring the roots down, so the root is always down. Do you get it? So if I have 36 1 over 2, I can write it as square root, and I'll bring the root in front of it, and I have 36 1. Another way, if I have 42 to the exponent 2 over 3, where is the root? The root is always down, so I can bring it as cube root, then I bring the root. What is left? 42 to the power of 2. So we can generalize that. We can generalize that anytime I have a to the power of a fraction, m over n, I can write it as root of, where is the root? This is the root, so n, and then a to the power of m. A to the power of m. So let's try an example. So let's say you are given 2 to the power of 2 over 3. You can write this as, what is the root? The root is 3. This is the root. The root is always down. What is left? 2 to the power of 2. That will give us root of cube root of, that will give us cube root of 4. That will be all for today. Join me in the next section as we solve a lot of questions that involves indices. Thank you for joining me, and as usual, like, comment, subscribe, and share to all your friends. Take care. Bye.